Welcome to my Commodore 64 Games memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have Skool Daze, published in 1985 by Microsphere Graphics, and title screen by Keith Warrington. I just have the tape version of this. I don't think there was even a disk version, so I need to convert this into a single program file, hopefully compressed, so I can load it into the C64 debug GUI, because the version of C64 debug GUI that I use does not really have tape support. It can load disks and it can load individual program files, but tape support doesn't seem to be there. So here's an opportunity to look at the tape loader. So I've noticed that the tape header actually just contains the file name and contains the rest of the blank data. This little breakpoint here is claimed initially, so the stop vector, which is at 328 here, is actually loaded by the kernel loader, and it starts calling some code at 2E8. Let's get the disassembly and the register windows open so we can more easily see what code is actually running. And we have this really intriguing code here. Look, the accumulator is loaded with F5 in hex, and then it stores it at 496 and then 328. So it's updating the, I think that's the stop vector at 328, right? It's updating the stop vector, and it's also putting a value at 496, which is minus. And then it's loading 496 and branching on minus back to, okay, so branch on minus. If it's a minus number, then it goes and returns. So the tape turbo loader, or not the tape turbo loader, the tape kernel loader, sorry, is actually calling the vector at 328 on a regular basis because it needs to check for things like the stop key and stuff like that. So the RTS is actually returning from this code that was just loaded back into the kernel loader and continuing on the load. However, when the value goes from, what was it, minus to positive, then it does a jump. It calls the other part of the code. The branch doesn't succeed, and then it calls the code at 400. So you can see, using my tape tool, I'm analyzing there the tape file, and the tape tool correctly indicates that it is using the stop vector at 328 and calling the code at 2ED, which is just loaded. However, the kernel is continuing to load extra code. It's not just this short section of code, but it's not getting there yet. It looks like, look, the code at 2F5 there is basically reading in what's on the screen. So when it loads over that particular point, then it's going to call that jump at 2FA right there, just underneath the cursor where it is now. And it's going to call that jump at 400 in hex. So the claimed stop vector basically detects when the load has reached that certain point, or probably just after it, because the stop key vector, I don't think it's called every single byte. I think it might be called every 5 or 6 bytes, maybe even longer, by the kernel routine. So yeah, that's an intriguing way of the loader to auto run its own code. I mean, it's basically interrupting the load. So on the Commodore 64, the kernel loader has 2 copies of the data. The first copy is loaded into memory. The second copy is then used as a verification test. And if the verification test fails, then you get the load error display on the screen. But what this does is that it detects that the data has been loaded into the screen memory or wherever, and then it starts calling into and running that code earlier than the verification pass. So you won't get a load error from this due to a verification failure, because it doesn't get to the verification pass. It actually starts calling the we'll see it in a second, it's an overload variant. There we go, as you can see here, the code loads. We could see that coming in on the debug graphics map there. And then look, that jump is hit, the jump to 400 in hex. So that's a really interesting way of doing an early auto start or auto run of the code. There are many different ways of getting auto running tape loaded, kernel tape loaded code to actually start running. This is certainly one way. It's a little bit convoluted. There are easier ways. Maybe they thought that it was a little bit of extra obfuscation to do it like this. Who knows? Anyway, so this is all part and parcel of trying to actually get at data which can then be saved for the game, for the single compressed program file that we need to get at to be able to run it in the C64 debugger. So let's continue on, because I need to find the end now of the load, and I need to trap it out just before the turbo loader now, which is going to be the Nova load, finishes loading the data and then runs the game code. So we need to get to that point now just before it starts running the game code. So let's step into the start of this Nova load variant for its turbo loading, and then we'll scroll down to see if we can find where the game start call is being used. This is just screen setup. D800, D900, D800 is color RAM setup, and I expect it's going to clear the top of the screen as well. It's actually filling the screen with spaces there. It's doing a whole bunch of default setup here, and then it's doing a final jump to 2A7. So we'll step into the code there at 2A7, and if we keep on looking down here, we can see that it's clearing the top of the screen, because now we're running code which is before the screen memory. And then there we go, we got a JSR to 800. That definitely looks like a slightly obfuscated game entry. It's actually jumping into code which hasn't been loaded yet, so that's a good indicator, right? That flashing border there, I think that's probably skipping the verification data for the kernel data, and now this is the turbo loaded data. Because although the auto booting code or auto running code for this variant of the Nova load starts running before the verification pass for the kernel load completes, or even starts, to be honest, it looks like the verification data was still saved out on the tape. And there we go. We are now at the point where the turbo loader is going to do that JSR to 800 in hex, which is 2048 in decimal, and that's the start of the game code. So yeah, there's JSR and other JSRs and load accumulators and stuff like that. Let's just double check what 01 is. 01 is the processor port which defines what banking mode the RAM and the ROMs are in, and the I/O space. So we need to make sure that we retain the value that's in 01, and what we'll just do here is that we'll just save out the whole memory, or practically the whole memory, but we need to make sure that we're saving out RAM, not the ROM or anything like that. And I want to restore back the value that goes into the processor port register at 01 in hex. It wasn't 37, right? It was just double checking again. It was 27. Yes, okay. So let's go back to bank RAM and then assemble a little piece of code here which just does a load accumulator with 27 and store it into the processor port, and then just do a jump to 800. We're not interested in returning back to anything because we're not going to. It's the game code. At this point, I can save the whole of memory, practically from 200 all the way up to FFFF in hex. I need to make sure that I note down what the start address is in hex, and that's the little bit of code that I assembled up at the beginning of screen memory there. A number of times I forget to specify device 0 in the monitor command for save to actually save to the PC's filing system, as opposed to device 8, which is the Commodore 64 disk drive, which is not connected. So now I need to use my little compression tool, which has some nice, fast, optimal compression. It's LZ based, as you might be able to guess, but it's been optimized for the Commodore 64. -C64 MBU is the C64 auto run code, so it puts a decompression code at the beginning of the program file, and MBU is max, border flash, and the ultimate compression method, which is the best compression method that I have in my tool here. And then if I run that output ctemp skd cmp.pig, it should just load, it should decompress, it should then run, and there we go. We have music, and we have the classroom coming in. Do you want to put in your own names? Yes, no. And there we go. The game is running. So now we can run this in the C64 debug GUI. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel, or sending me a super thanks. They are always very much appreciated. Here we are in C64 debug GUI now. I'm just loading that compressed version of the tape game. There we go, it's started again. So when the screen scrolls on and it asks us the question, don't want to put in our own names, or own name rather. Let's just start the game. Now, immediately we can see that there aren't any sprites visible. We can see that it's in bitmap mode, it's in high res bitmap mode. We can see that the bitmap data there is consistently at E000, there's only a single buffer. So we don't have any hardware sprites visible because there are no red bounding boxes currently on the screen, but we have all of these walking around characters. Okay, that's going to be intriguing. So we have some software sprites using a single buffer bitmap mode in this game. And that probably really explains, one, why it's looking a little bit color clashy, and two, the frame rate, which, to be honest, is not great for this game. Let's move all of these debug windows out of the way so we can see the full screen. Now, if I move around a bit, my little player character is moving around there. Now, because it's in high res bitmap mode, we have a background color and foreground color for an 8x8 pixel character cell. And because it's software sprites, that's why we're getting color clash. Oh, look, that's interesting. We're using hardware sprites for the messages that come up on the screen. Ah, there we go, you see. If I change the color of the sprite when it's being rendered there in the debug view, we can see the text there. So the white text now appears in front of a solid block of color. So the solid block of color is actually in the bitmap. But the text itself is actually sprite, hardware sprites, over the top of that. Okay, well that's certainly one way of removing the issue of color clash for the text messages, and probably also the speech bubbles as well. Now this view here in the middle of the screen, here we got that pulsating purple blob rectangle, but these little blue blobs here indicating memory reads are corresponding to the positions of software sprites. Software sprites that are actually currently visible on this section of the screen here, look. And correspondingly on the left hand side as well we have similar coloured blue blobs there. So that seems to indicate that we have two. Now these blobs are not large enough to correspond to full bitmap data. There's probably the background, the bitmap colour screen data, right? Or like an off-screen copy of it. Now this memory view is 256 pixels wide, corresponding to 256 bytes per memory page, and there are 256 memory pages. 256 times 256 is 65,536 bytes, which is 64 kilobytes, because a kilobyte is 1024 bytes. In the Commodore 64, we have 64 kilobytes of main RAM, give or take. There are a couple of bytes at the beginning that can't really be changed by the CPU, and then of course we have the color RAM, which is a 4-bit RAM. But basically, we have 64 kilobytes of main memory. Those speech bubbles, look, the speech bubble there is hardware sprites in the middle of the screen. So that's interesting. The game, as we can see, is mostly using software bitmap sprites with hardware sprites for the speech bubbles and the text messages that come up from the teachers and probably the pupils as well. I never really got on with this game when it came out. I don't think I had the instructions, and for various reasons. And I didn't really understand what you were meant to be doing. And to be honest, the low frame rate also wasn't really interesting. I really preferred more arcadey type games rather than this type of game, to be honest. So let's have a look at this now in ICU64 to see if we can understand a little bit more about the game's software sprite rendering. So here we are in ICU64. Let's look at the memory view here. Let's zoom in. And if we zoom in a little bit more, we can see that the memory address there is 7C86, for example. So we know the rough area in memory. And these green blobs definitely do, and the green blobs indicate memory reads. Okay, so the memory for these green memory blob reads here is just being read. So that indicates that there is no commit to the off-screen buffer of writes as such. It's just reading. So it's refreshing the screen data or color data just from this area here. And those green blobs correspond pretty well to the blobs. There we go, there's a nice diagonal line there as the player character was, or rather one of the characters was walking up the stairs. There we go, there's a whole bunch. And we can see there that there's some nice diagonal lines. This yellow and green update in the middle, the rectangular blob there, in the middle of the view, indicates writes and reads going on. We can see there's the bitmap mode there's the bitmap view way up at the end of memory, which is an unusual choice because it's going to be at the last half of the last bit bank, so it's at E000 onwards. It's practically underneath, well, it is underneath the kernel. It's the RAM underneath the kernel ROM, so you're hitting that all the time. On the left-hand side as well, we seem to have similar patterns of those green blobs, those green memory reads. So we have two kind of like off-screen buffered copies, basically, of what probably looks like the same color data, right? Yeah, because it's it's slightly less than 128 bytes wide, looking at this, because there's 256 bytes horizontally, right? So that yellow and green rectangle is taking a chunk out of the 256, and so we divide by 2, it's slightly less than 128. So there we go. We use a watch point to see what is actually reading from that memory address, which was being highlighted in green, where it was reading, and we can see this code here was accessing that memory for the green blob. And we can practically immediately see that the green blob data is being accessed by this code. Let's update the debug notes. So we have it's spaced by 128 bytes offset, these two rectangular left and right halves, right? But I think it's probably just the buffer, obviously, in the screen is vertically oriented, right? But we have two shorter buffers, if you like, so it can put them adjacent in memory. But I think, looking at that, those green blobs were 3, 4, 5 bytes tall, which kind of indicate, the larger ones anyway, so it kind of indicates that they are restoring data for the current level map, which is in memory, right? But I think it's probably restoring data that corresponds with the taller teacher characters or entities, if you like, rather than the smaller pupil entities. That's an intriguing routine, though. I think we need to look into this into some more detail to really understand what this code does. So since we know where the bitmap data is, it's going to be at E000 onwards, we can have a look on the memory watch point for storing into the bitmap data to see what code is actually updating the bitmap data itself. And we get to this routine here at 321B. And having a look at this routine here, it seems to be, if I understand it correctly, the code at 333F there was doing some bitmap operations, so loading and storing data from some off-screen data buffer and then updating it into the bitmap data itself. So reading from 7C23, which is indirected at 52 there, and then it's storing to CCBB in this case, which is actually the bitmap color screen data. So we know we now know for certain that those green reading blobs that we were looking at in the memory view just now are definitely bytes of data which are for the screen, or color data for the bitmap. So although it's technically the screen data in high-res bitmap mode, the VIC uses the screen data as color data. Okay. The reason why it doesn't use color RAM is because color RAM is only 4 bits wide, but high-res bitmap mode needs to have 2 lots of 4-bit color information, so it puts that into 1 byte, which is coming from the screen data. You'll notice here at 333D that Y register is 80 in hex, which is 128 in decimal, and then at 3341 Y is set to 0, and this reads the right and the left hand portions of that area in memory where the green blobs were appearing. So it seems that it's basically restoring the color screen memory from a backup, but it's then reading the color memory that it needs to use for the software sprite and putting that into 5.4 as some temporary working area. I wonder why it puts it into 5.4 in 0 page as temporary working area, but we'll figure that out in a bit. Just updating my debug notes of what we've discovered so far. So tracing back through the bitmap rights led me to this routine here, the beginning of this routine here at 3.1 If I put a breakpoint here and then advance each frame, each breakpoint, but if I noticed that this routine here was reading pre-prepared data from this large, this 128 bytes worth of table when it was doing that render. So when it was doing the bitmap and the color bitmap screen render. So I noticed that if I fill this table here, this temporary working space, with 0, and then if I allow this code to run, filling the tables with 0 means that the code still runs, but it doesn't draw anything on the screen. And this was found by tracing back through a watch point for the bitmap draw. So this tells me that there's quite a lot of calculation going on in the background to fill or to prepare this data table with values that is then used for the entire screen frame draw. Okay, because if I use the X command here, we can see, look, it's doing the green blob reads, it's then refreshing the view for the screen, and then it goes into the next frame. So this does the screen rendering, but it all does it in one pass, and it's doing it from a lot of pre-prepared or pre-calculated data that goes into this table at 4012 all the way up until 40 what is it, 7F or 6F or something like that. So we can see there it's doing a load indirected with 4E, and then it basically erases the pre-calculated data as well once it has finished processing a character cell in the bitmap screen. So this tells me that the game is actually doing quite a lot of pre-calculation into this buffer here at 4012 to 407F. But it's doing that to prepare the draw for the screen, and then it's doing the draw for the screen all in one pass. It's probably doing that to reduce flicker. It's because it's using a single buffered bitmap screen mode. It is also probably doing that because it needs to do quite a lot of pre-work or pre-calculation work to actually create this this buffer in the first place. So what is actually storing into this buffer? Because that's where the real kind of like, rendering calculation logic is going to do, right? So after the render routine at 3.1 completes, I'm going to look using that particular watch point to see actually what code calculates into that buffer area of memory there, 4012 to 407F. Let's see what that code is. You can see here, look, it's doing a load or with some data that's being calculated and then storing it back in there again. Okay. Maybe, I don't know what this data table structure actually is, but it might be some kind of like flag value or something like that. So anything which is non-zero indicates that this bitmap renderer needs to do something for that particular point in the screen, and then it reads back from some other data table the actual precise thing that it needs to do. tracing through the game update loop got me to this point here, and we can see that there are 4 JSRs to 3 AB4s in a row, and then a jump to 916. But there's also another bunch of JSR to 3 AB4s. Now, when I was looking through the execution for this, every time I step over 3 AB4, there seems to be some memory updates going on in the middle of memory. But it's not doing a screen render. Now, if I get rid of most of the JSRs, okay, at 3AB4 by using a no-op here, then it is not going to be calling the routine at 3AB4 as often. Basically, I got to this point and I noticed that, that load A with 2B test is actually succeeding or not, depending on whether or not the weapon's being used. But look, now the game is actually updating a lot slower. When I remove those superfluous JSRs, the game was moving a lot slower. So let's just run that again. Look. So the game update is still running, it's just running 4 times slower. So each one of those JSRs to that routine is actually running 1 iteration of the game update loop. You can see how quickly it runs when I restore the snapshot. So why is the game running 4 times the game update loop for 1 game render? Because 3AB4, that routine there, doesn't render to the screen. It was just updating the pre-calculation buffer. That's really intriguing. So the game update loop is being called 4 times as fast as the bitmap render. Wow. Okay, maybe the programmer realized that the bitmap render is so slow that they need to increase the iterations, or the number of times that the game update loop gets called before it gets back to this JSR to 3.1 there, which draws the game screen. So that's the way that they tweak the apparent speed of the game, is to actually just run the game loop 4 times faster than the render. Wow. Well, that's really very unusual, right? The game update loop does quite a lot of calculation, calculating into pre-calculated buffers and stuff like that. That then the bitmap render reads. Wow. So all of the software sprite updates get accumulated into this buffer that then the bitmap render then processes and actually updates on the screen. Wow. Okay, that's very, very unusual. So here we are back at 3.1 which is the routine for rendering into the bitmap. I'm going to fill the memory that's used for the bitmap with all the zeros. Okay, so I'm going to basically clear the bitmap screen, leaving the score panel down at the bottom mostly intact, I hope. There we go. So we'll just use that memory range there, and there we go, that's good enough. So advancing 1 frame, wow, look, you can see there in the graphics map view that the software sprites gradually get reintroduced. So this definitely tells us now that the game is using only a dirty rectangle update. And actually not all software sprites were being rendered for each frame as well. Well, that kind of makes sense, right? I mean, if a software sprite doesn't change frame, doesn't change position, you don't want to redraw it, right? Because nothing has changed on the screen. So for speed purposes, you don't want to redraw what hasn't changed. But look, you can see the trails going around. This is the debug graphics map makes it much more apparent because there's no color clash or anything like that. But you can see where the screen has updated with the software sprites, then that's what's being restored. So all of this screen data memory is being held somewhere in an off-screen buffer or some off-screen buffers somewhere, and then only being restored on a piecemeal basis, on an as-needed basis by the screen renderer itself. So let's clear that memory again. There we go. See, look. Wow. Yes, definitely. It's using a nice... Okay, so that's really quite cool. This game is using a nice optimal dirty rectangle. It's called the dirty rectangle because basically the dirty rectangle means that you're only restoring or only rendering the portion which is inside a rectangle which you need to render. And that's because rectangles are just basically a common, quite easy unit for a computer to deal with. So yeah, what you're basically updating, you're only touching that area on the screen. So it's more optimal to do it like that, as long as you don't spend more time on doing all of the non-visible pre-calculation work. Okay, if your bitmap draw is, or if the time saved in the bitmap draw is more than the time cost of doing the pre-calculation, then it's going to be quicker. However, if you spend a lot of your time doing pre-calculation and your bitmap draw is not that expensive, then you're going to be losing time. Okay, so it's a cost-benefit analysis, but generally speaking, it's if you're not updating much of the screen per visible frame, then it's a lot quicker to use the dirty rectangle method. If I clear the screen and then advance one rendering frame, we can see that the teachers and the pupils. Now, that's really intriguing. Look, you see, not all of the pupils and not all of the teachers are rendering every single time I advance one frame of the render. So that really is quite an optimal dirty rectangle. Basically, it's not rendering every single software sprite each frame. It's only rendering the things which change each frame, which is really quite cool. That's actually something that I do really like, is a nice optimal dirty rectangle software sprite draw. One last thing I want to have a look at is this yellow and green rectangle blob that's appearing in the middle of the memory view there. I really want to try and understand a little bit more about what that is. This area here is the memory range at 4000 in hex, which was basically the pre-calculation area. But this area here, look at that, right? This blob of memory here. Now look, you see, all of the characters have disappeared, all of the entities have disappeared, and it was basically zeroed out. You know what I think this is? I think this is the game logic, game entity state area in memory. Yeah, letting the game run. Yeah, look at that. See, when reverse engineering something, looking at this, you kind of get a feel for the pattern of the data, reads and writes. Yellow indicates a memory write, green indicates a memory read. Looking at what is on the screen compared to what we're seeing in this debug view here, I really do get the very strong feeling that this is entity information. This last line here is continuously updating in a different pattern compared to the ones up above it. there's always a constant pattern of reading and writing, whereas the ones up above it are going in a kind of like a ripple pattern, right? Maybe the ones up above it are for the pupils and the teacher. Maybe the last one is for the player character, because the player character updates every logic step, right? You see, look, this first value here, the 8.2 value that I'm currently looking at, is not changing, and 4.7 and 0a are not changing as well, but they're constantly being accessed every frame, or every game update tick, if you like. Let's change that first byte there to be 0. Nothing has visibly changed on the screen, but look, when I move the player character, it's restored back again, and it's okay. So if I put 0 in there and then I move, let's put 8.0 actually. Okay, it doesn't change what's visible on the screen. Okay, well, because of the dirty rectangle stuff, the dirty rectangle stuff hasn't realized, I think, that the animation frame has changed. 8 is changing the number between 0, negative and positive, right? Because it's the high bit, so I'm betting that that's a horizontal flip for the software sprite. We've seen this kind of thing before, right? A bit is being used for the horizontal flip. Let's change the second value to be, oh look, the player character X position changed, and the dirty rectangle routine basically left what was on the screen there before until I actually went running over that area. Yeah, so now when I change the X position, I seem to be completely off the left-hand side of the screen. Let's change it to 40. And there we go. My player character has reappeared again. Let's change it to be 20, right? And then that seems to be a bit too far off the screen. Perhaps let's change it to 30. And then, hey, there we go. There's my player character again. So I have the old version of the player character and the new position of the player character on the screen simultaneously until the software sprites for the pupils, one of the pupil entities, come along. Okay, so this definitely looks like entity state information. So the first byte is the animation frame, plus also a bit to indicate whether or not it's flipped left or right. And then we seem to have an X position. I'm betting that the other one is Y position, for example, because the Y position doesn't change that often. And so that's the last thing that I wanted to really understand in the game, is where the entities are and how the game manages the entities. In this video we've looked at the software sprite rendering and how it uses an optimal dirty rectangle, if you like, to reduce the screen draw for the game, and also how the game uses hardware sprites for these messages that come up on the screen, but also the speech bubbles and stuff like that. So thank you, as always, for watching these crazy retro games memories videos. If you like this kind of stuff, then please do consider liking or subscribing to my channel, and I really hope to catch you around next time. Take care, have a great day or evening or night, wherever you are.